Hello class, this is a continuation on recurrence relations. In the previous video we saw how we could just simply operate the recurrence relations. But now you can see that from some of these examples we can see that some recurrence relations, they form an arithmetic progression or a geometric progression. We now just need to learn how to convert between a recurrence relation of this form into a geometric or arithmetic progression. So, given the expressions, let's go straight into an example here. Given the expression for an arithmetic progression or geometric progression, write these as a recurrence relation. So these are APs. Let's find the GP. Let's find the recurrence relation for this. So for this one, the best way you can do it is find the first few terms. So let's say we find T1. T1 is substituting 1 here. So 2 times 0 is 0. So the first term here is 3. The next term, substituting 2. So 2 minus 1 is 1. 2 times 1 is 2, plus 3 is 5. And I'm sure you can already see that it's going to increase by 2 because the common difference is 2. So 3, 5, 7, 9, dot, dot, dot. So now to make this into a recurrence relation, we can simply say, well, it's always going to be t of n plus 1. So the next term is given as the current term, but notice now what it's going up by. Well, the current term plus 2 gives us the next term. The current term plus 2 gives us the next term. So in this case, it's just t of n plus 1 equals the current term plus the common difference 2. But for this, we always need to state that the first term is 3. And this here is our recurrence relation. It's pretty simple. Let's move on to the next example. So for this, well, let's find the first few terms for this one. We get the first term is going to be, A, it's not going to be there, it's going to be half. The next term is going to be the negative but double of this, because the common ratio, because remember it's AR to the power of n minus 1. The ratio is 2, so it's doubling each term. So the double of half is 1, but because the ratio is negative, it's going to flip back and forth between positive then negative. Next one's going to be positive, so doubling the previous, so 2, and doubling the previous of this is 4, but it's negative, dot, dot, dot. And of course you can check this by substituting into your calculator. But now, and I hope you quickly saw a relationship between the recurrence relation and these APs or GPs. To find the next term, we take the current term and we multiply it by -2, because that's what the common ratio is from one to the other. Because look, from this term to this term, that's times -2 times -2 times -2. By writing this out, we can see, well, to get the next term, we take the current term and multiply it by -2, which is what we've written here. Oh, and I forgot to state that the first term must always be stated t of 1 equals half. And there we have it. Now, going backwards, so given the recurrence relation, find the expression for any term in the sequence. Well, it's always good just to start making the first few terms. T1 is -3. The next term is -3 substituted plus 2. Well, -3 plus 2 is -1. -1 resubstituted plus 2 is 1. That's enough for us to make a progression. Well, for this to get the t of n, so any term is given as a, which is the first term. Oh, and I hope you quickly saw that it's just going up by 2, so it's a arithmetic progression. So -3 plus 2 bracket, well, n minus 1. We can simplify this further if you'd like. We get -5 plus 2n. So I just expanded this and collected like terms. So it's not too difficult going back and forth between a recurrence relation and a progression notation, AP or GP. One more for this. The first term is going to be 1/8. The next term is going to be double that, which is a quarter. Double that is a half. Double that is 1. So for this, to get any term, t of n, we get a, which is 1/8, times 2 to the power of n minus 1. And that's pretty much all there is to it. If you really wanted to simplify this, this will become 1/8 2 to the n times 2 to the power of -1, just expanding those index laws. This becomes 1/2, which will give us 1/16 to the power of times 2 to the power of n. But I hope you could easily identify this one. Now, before you, or if you had any questions on this, a common one is asking, do all recurrence relations become an AP or GP? Well, the answer to that is no, it doesn't. Because if you take a look at these ones here, it goes up by 4, and then it goes up by 8, and then up by, up by 24. So there's no common difference, and certainly 0 times anything doesn't give us 4. So there's no common ratio. So this is neither an AP or GP. Likewise with this one. If you try and find a common difference or a common ratio, there won't be one. So recurrence relations sometimes become an AP or GP. So I hope that gave you an insight into recurrence relations and their relationship to APs and GPs. Hope to see you in the next video. Best of luck.